For billions of years, one star has fueled all life on Earth, our sun. Its light warms our oceans, feeds our forests, and powers every breath we take. At its heart, deep within that blinding inferno, something extraordinary happens every second. Fusion. The process that makes stars shine. Fusion is nature's ultimate power source. Tiny atomic nuclei, hydrogen atoms, collide and merge, forming helium. In that moment, a fraction of their mass transforms into pure energy, as described by Einstein's famous equation, E equals mc squared. That's the same process that lights up every star you see in the night sky. For decades, humanity has dreamed of capturing this power, not as a weapon, but as a source of endless clean energy. Imagine the energy of the sun recreated safely here on Earth. No smoke, no carbon, no endless fuel consumption, just the brilliance of physics itself. But turning that dream into reality has proven to be one of the most ambitious scientific challenges in human history. From the moment our ancestors discovered fire, humanity's progress has been powered by energy. We burned wood, then coal, then oil, each step fueling new revolutions. The steam engine transformed industries. Oil powered the 20th century. Nuclear fission split atoms and reshaped geopolitics. But every breakthrough came with a cost. Burning fossil fuels filled our skies with carbon, warming the planet and polluting our air. Nuclear fission gave us enormous power, but also fear. Fear of radiation, waste, and weapons. As our population grew and our appetite for electricity surged, one truth became unavoidable. The way we generate energy cannot continue as it is. We need a source that is clean, safe, and abundant. Something that could sustain civilization without destroying the planet that sustains us. And so, the gaze of science turned once again toward the stars. Fusion, like the joining of atomic nuclei, is the opposite of fission, where atoms are split apart. While fission leaves behind long-lived radioactive waste, fusion is astonishingly clean. Its primary fuel, hydrogen, is found in ordinary water and seawater. Just a few grams of hydrogen could power a household for years. To achieve fusion, scientists must recreate the conditions inside the sun. Temperatures over 100 million degrees Celsius and immense pressure. At such extremes, matter transforms into plasma, a glowing soup of charged particles. But containing that plasma is like trying to hold lightning in a jar. No physical material can touch it. It would vaporize instantly. That's why scientists use magnetic confinement. Powerful magnetic fields that suspend and twist the plasma inside a vacuum chamber shaped like a donut called a tokamak. Inside that magnetic cage, hydrogen nuclei are forced together at incredible speeds until, for a fleeting moment, they fuse, releasing more energy than they consume. If we could sustain that process continuously, we would unlock the same power that fuels the stars. The dream of fusion began in the aftermath of World War II. Physicists who once harnessed atomic fission for bombs now sought a way to use nuclear science for peace. In the 1950s, Soviet scientists developed the first tokamak, achieving glimpses of plasma confinement. The word itself comes from the Russian phrase toroidal chamber with magnetic coils. Throughout the Cold War, fusion research became a global effort. The United States, Europe, Japan, and the Soviet Union all built experimental reactors, each a little better than the last. But progress was slow. The technology required materials and computing power far beyond what existed at the time. By the late 20th century, optimism faded. Fusion was always 30 years away. But behind the scenes, scientists kept pushing. Refining magnets, learning to tame plasma instabilities, and developing new superconductors that could handle unimaginable forces. Every small victory brought us closer to the star. In a quiet corner of Provence, France, humanity is building the most ambitious scientific machine ever conceived. ITER, the International Thermonuclear Experimental Reactor. It is a collaboration between more than 35 nations, including the United States, China, India, Japan, Russia, and the European Union. Together, they are constructing a reactor designed to demonstrate the feasibility of large-scale, sustained fusion energy. ITER is not meant to generate electricity for homes. Its mission is proof to show that fusion can produce more energy than it consumes. If successful, it will generate 10 times the power needed to heat its plasma. The scale of ITER is staggering. Its central magnet, called the central solenoid, weighs more than a fully loaded Boeing 747. Its plasma chamber will reach 150 million degrees Celsius, 10 times hotter than the core of the Sun, all contained by magnetic fields 100,000 times stronger than Earth's. It's not just a machine, it's a symbol of what humanity can achieve when nations cooperate for a shared dream. If ITER succeeds, it will mark the turning point in our quest for infinite clean energy. While governments build ITER, a new generation of dreamers is taking fusion into their own hands. Private companies, agile, innovative, and hungry for results, are redefining what's possible. Startups like Commonwealth Fusion Systems, Helion Energy, and Tokamak Energy are racing to build smaller, cheaper reactors using cutting-edge materials and artificial intelligence. High-temperature superconductors now allow magnets to be more powerful and compact than ever before. Some approaches use laser-driven fusion, like the experiments at the National Ignition Facility in California, where in 2022, scientists achieved something historic. For the first time in human history, a fusion reaction produced more energy than the fuel absorbed. It was a glimpse, a proof that fusion ignition is possible. The era of fusion is no longer theoretical. It has begun. Private pioneers believe they can bring commercial fusion power to the grid by the 2030s. If they succeed, the world's energy landscape will never be the same. Imagine a future where power plants don't burn fuel, don't emit carbon, and don't rely on the wind or the sun. A future where energy is so abundant that scarcity becomes a word of the past. Fusion offers that possibility. Its fuel, deuterium and tritium, can be extracted from seawater and lithium. A single glass of seawater could, in theory, provide enough hydrogen to power your home for a lifetime. Fusion reactors produce no greenhouse gases, no long-lived radioactive waste, and no risk of runaway meltdown. When the reaction stops, it simply cools down, like turning off a light. If humanity masters fusion, we could eliminate much of the world's energy inequality. Deserts could bloom. Developing nations could power their economies without pollution. Electric cars, desalination plants, and entire smart cities could run on the same principle that powers the sun. But challenges remain. Building and maintaining a fusion reactor is complex and costly. The materials that face the plasma must withstand neutron bombardment for years. The fuel tritium is rare and must be bred within the reactor itself. Still, progress is accelerating faster than ever before. With each experiment, with each spark of plasma, we inch closer to an energy revolution. Fusion won't just change science, it will reshape civilization. An unlimited energy source could shift global power structures. Countries rich in oil or gas may lose their leverage, while those investing in technology could rise as new energy leaders. Economies might transform overnight. With abundant power, we could lift billions out of poverty, but we must also ensure that fusion doesn't deepen inequality. Will it be shared freely or patented and controlled by a few corporations? Will it unite humanity or divide it further? Fusion's promise is immense, but so is our responsibility. Energy is not just a scientific question, it's a moral one. How we choose to use this gift will define our future. Every great leap in human history began with an impossible dream. Flight, space travel, the decoding of the human genome. Fusion is the next chapter in that story, perhaps the most profound of all. Right now, in laboratories around the world, the first artificial stars are being born. Tiny suns, held within magnetic fields, burning brighter than anything humanity has ever created. Each one brings us closer to a world powered by starlight. Someday soon, When we flip a switch and our cities glow with fusion energy, we'll remember this journey, the decades of struggle, the scientists who refused to give up, the nations that came together in hope. We will look up at the sun and realize we no longer just receive its light. We have learned to make our own. And when that day comes, humanity will have crossed a threshold from being the children of the stars to becoming their creators. We've reached the end of another video, friends. If you like this video, don't forget to like it. We'll learn a lot from the videos I share. Don't forget to subscribe to my channel so you don't miss my new videos. See you in the next video.